Hey Bob, how you doing?
Dandy, how are you?
I'm good, thanks. It's nice to see you.
Nice to see you too. Funky background you've got. Very architectural.
Yes, mandatory, I'm afraid.
Oh, they make you do that one?
Yeah.
Or just
Well, we
any
have
one?
a few. We just have a few different ones. You can pick one.
I see. There's a
Yeah.
corporate image person in charge and
Yeah.
okay.
Yep. Alrighty. I am keeping track of the waiting room. I'll give it just a couple of more minutes.
Good.
Um,
I'll make sure. Let's see. You're just seeing me right now, right? Is that correct?
yes,
Okay.
correct.
How do I switch over to the presentation? Chat participants.
Share and
Stop
the
video? Audio. This is an odd looking screen I've got with you right now. Let's see. Let's make you bigger. Maybe I can get it from there. Participants, video, chat. Ah, there's share. Okay, good. Share is not turned on. Send request. There we go.
oh, there you go. Allow.
Thank you.
Yes, of course.
If I were to share now and I were to go to an entire screen, but PowerPoint slideshow and share. All right, you seeing the slideshow now?
Yes.
Cool.
Hmm.
And slideshow, go back to video for the things I need to do for that. And then, oh, I know what I needed to do. Oh, spies. Let's see. Do I have those other windows open? Good, got that one open. Let's see. And if I did that one, oh, cool. And then that one. All right. So it goes back up. And then if I go tab back to the slideshow and shrink that. Are you still seeing my slideshow?
Yes.
Okay, good. I think I've got everything set.
Okay, perfect. Looks like we're right at the start time, so I'll keep an eye on the waiting room and let anybody else in if they need to be. But hi everybody, my name is Gina Morgan. I am the secretary for IES RMS and I work at Illumination Systems if I haven't met you before. I believe you guys are familiar with Bob. He did the training last time, I see. So this session's topic is going to be metrics. So it's going to be really interesting. It's going to be great. Let me know if you guys need anything while the meeting is running. Otherwise, I'll just take attendance. The last thing to let you guys know is that the in-person session was scheduled at New Light, but they are having some power issues. So it has been moved to TLA's office. So if you guys need that address, it should be an easy Google. But just again, in-person session is now going to be located at TLA. So anyways, I won't take away any more time from your presentation, Bob. Take it away.
All right, can everybody hear me?
Yes.
Good. And you're all looking at the slideshow, right?
Yes.
Cool. All right, so here we go. So last time I talked to you guys, oh, actually, you know what? I had a couple things I wanted to bring up real quick from the last session. Let me see. All right, so if I end slideshow, okay, and I try to share something else, I wanted to show you something real quick. If I can find it. All right, here we go. All right, so one thing we talked about sources last time, and remember how I showed you that LEDs use a blue chip, and then you paint phosphors on it, and you re-radiate it back out into the spectrum. Can you guys see? Let's see make sure I'm doing that right. Can you see the chart that's in front of me? It says L90 9 watt on the top of it.
Yes.
Yeah.
You can. Excellent. All right. So if you take a look at the bottom of that chart, right, you look at this is a stick of a 1 foot stick of a fixture that can come into a bunch of different color temperatures, right? And remember how we started with blue and we put phosphor on it and we re-radiated down into the visible spectrum. Notice how many lumens that you get at 4000 K, right? And let's just look at the first column in the tight beam, right? The 10 by 10, you get 714. You take that farther away from the blue, right, into 3500, you get 684. You take it farther away from the blue into 3K, you get 674, and even further away from the blue into 2700, and you get 639, right? So 80, almost like a 10% loss to go from 4K to 2700. That used to be even larger difference, but it's something to take into account sometimes when you're talking about color temperature and lumens, in that a lot of cases, when you go to warmer color temperatures, you're going to get fewer lumens. And so if you have a certain foot candle number you're after, then you might have to increase the number of lumens you throw at that at X color temperature to get to that foot candle number. And we're going to talk about these units today. So I wanted to make sure that I did that stuff. All right, so we're going to stop sharing that one. That was just a little thing from last time, right? And now we're over here, but I failed to mention. Let's see here. I think now. All right, you guys seen the slideshow again?
No, it's just the screen.
No. Okay, so what am I doing wrong? Hold on. Let's see, let's make that. Let's go over here, escape. All right, what am I doing? Oh, there it is, maybe. And hit share. Nope, that's not working. What did I do wrong? Let's see here. Put it there. Let's go here, tab. Share. And all right, how about now?
Yep,
Cool. All right. Someday I'll learn this stuff.
all good.
All right. So here, the beginning messages and all that stuff. You guys are going to get credit for attending these sessions, et cetera, et cetera. And here's my module, metrics, photometry, calculations, and renderings. Now, all right. So when we talk about light, there are a lot of different ways to describe light and which way it's going and where it's headed, how much of it there is, that's coming off of surfaces and all that kind of stuff. So there are a lot of different metrics involved in lighting. When I took my first lighting class, I was so confused. I ended up having to have a cheat sheet in front of me on my lap that describes all of these things we're about to go over so that when my professor talked to me, I could figure out what the hell it was he was talking about. Okay. So don't feel at all uncomfortable if you don't grasp every single one right away, but they're actually easy to understand once you write them down and once you look at them. Okay. So we're going to talk about those things. We're going to talk about how they relate to real life fixtures, and that's through their photometric reports. And then we're going to talk about how we calculate using those things to figure out how much light we're getting onto surfaces, which in the end is a lot of what lighting is about, right? We want to put light places. There are many artistic parts of lighting. There are many aesthetic parts of lighting, but we're kind of getting into the meat of how many foot candles do I have, and is that enough to meet the task that we're trying to accomplish? So this is a very math-oriented part of lighting. There's a lot of artistic-oriented and visual effect-oriented stuff that we're not even touching on, right? We're just trying to track lumens around, and that's what I do for a living, so it works out pretty good. All right, here we go. So photometry, right? Metrics, meter, photo, light. Photometry is what we talk about and is how we interact with our light sources as humans. Not necessarily is how the light sources put out light across the spectrum, because our brain is involved in the process, right? So there's some differences between radiometry, or how much light that fixture puts out, and even across, say, light, right? We have a definition of what light is. It's what we can see. Maybe that fixture's putting things out beyond light, right? Into the UV or down into the IR, which radiometry would all take care of. But photometry is the science of looking at that output across spectra, running it through what the human eye brain system does, and talking to us about how much light that thing puts out. Okay. And that's about what we just talked about there. And here are those things that I ended up on my piece of engineering paper on my lap as I watched my professor talk to us. Okay. Um, Luminous flux, the lumen. You'll hear a lot about the lumen. I call myself a lumen counter, right? You can think about it as droplets of light if you want to. In the end, what it's really about is a measurement over time of how much intensity is put out across that spectrum that people look at, right? But if you think about it as drops of light, we can move on from there, right? Luminous intensity. How many of those drops of light are going out into a cone, starting from the source out into space forever? Right? That's intensity. That's lumens per steradian, essentially, is what a candela is. And we'll talk about what a steradian means too. Illuminance, when you take that drop of light and you drop one of them onto a square foot, or when you drop one of them onto a square meter, that's what we call illuminance. And that's the thing that we most track. How much light are we putting onto a surface? Because it's easier to track that. You can work from photometric reports and things like that and get, no bounce information, very accurate as to how much light's going to hit a surface by way of using those photometric reports and our formula that give us that, right? So illuminance is easier to talk about than if you then use that illuminance, you incorporate reflectance into it. How much of that light that hits that surface bounces off? And in what way does it do that? And that's the key, right? For then the other two things on this list here are luminous excitance. That is valid only for diffuse surfaces. And so if you think about luminant or illuminance, right, going onto a surface, so 1 lumen per square foot, if you have that square foot be diffuse, tissue paper, chalk, concrete, most of the time, something like that, and it has a certain reflectance value, then you take that, how much goes on times the reflectance value, you figure how much goes off. But it always goes off in a very diffuse manner, right? So it's an easier calculation. You don't have to think about geometry and angles at all with a diffuse surface. And so you have this special case called luminous excitant, which keeps track of how many lumens bounce off of a diffuse surface, like tissue paper or chalk. Then luminance, now that's very specific. If you come back to that piece of tissue paper, chalk, or mirror, or whatever it is you're bouncing light off of, and you take a luminance meter and you shoot back at it, you find out how many lumens per steradian per square meter there are coming off of that thing, right? And so that ends up running through your brain and it ends up being interpreted as brightness, right? Luminance is the physical counting of things. Brightness is your brain's interpretation of that luminance. Okay, and here are a bunch of things talking about all those things we talked about, right? Down to a little bit more detail than we're probably going to get into today, right? But we talk about these things. Look at lighting condition, illuminance, lumens per unit area, either be a square foot or a square meter, and that's what foot candles and lux are, right? And then luminance, candela per unit area. How many lumens per steradian are coming off of that square, whatever it is, and that depends on your view angle and all the reflectance characteristics of the actual surface that you're looking at. Reflectance, transmittance, light comes through stuff, obviously. Although most of the time, as lighting calculation people, we are counting light bouncing off of things, not light coming through things. It's a little more difficult to count light coming through things because it often changes the way that the light comes through that thing. And how do you keep track of that? Again, really hard. So we tend to count reflectance values, we tend to count light coming off of fixtures, and we tend to account for how much light is hitting a surface, but then we don't typically talk about how much light is coming off of that surface. So my standing desk is black, and I can put a illuminance meter on there and tell you I've got, I'm guessing on what my hand looks like now, maybe 12 or 13 foot candles, right? And then you talk about it maybe being a diffuse surface, and that black is all of 5% reflective. So take 10 or 13 times 0.05, and that's how many, let's see, what did we call excitants? Foot lamberts, right, are coming off of that surface. Now, if my standing desk had been white instead of black, maybe that reflectance value was 0.8 instead of 0.05, and my standing desk would look a lot brighter. Well, that's kind of common sense, right? But it's something to keep track of when you think about how we account for light in a space. Typically, we're accounting for what goes on, not what comes off. Okay, move on. All right, then how do we put all that stuff into play? Well, you would have a light fixture, you would measure its output across an entire hemisphere or sometimes a full sphere. And the way that you did that is you made that fixture act like a point source, and you had a illuminance meter far enough away from it such that it would act that way. And you would take all these measurements all the way around, right? From straight down to straight to the side. And then in plan view, going all around the fixture, always bouncing this light off the mirror over to that photoreceptor over there. And then what they would do is you would backtrack that illuminance number into a candela number, the intensity that it would take to make that many foot candles from that far away. You put it into a table and you have a photometric report. Now, the way that photometry was done, and again, just like last time, I'm going to jump around a little bit. They had relative photometry is what they called it. So you had these numbers, you summed them up with zonal constants into a sphere of quasi lumens, if you want to call that. And then the manufacturer of the lamp that's inside that fixture gave you a number of what that lamp put out. You compared the two, that was called relative photometry, and you could come up with an entire report. Now, with LEDs, we've moved on a little bit from that, and instead of trusting the lamp manufacturer to give you a number of how many lumens that thing put out to start with, oh, and you measure the bare lamp on its own as well. Okay, so you measure the bare lamp, you figure out those quasi-lumens. You measure that lamp in the fixture, you figure out those quasi-lumens. You do the ratio, and you kind of have your photometric report, right? That's called relative photometry, assuming that lamp had, if it was a T8 lamp, like 2,900 lumens. Right? That's how you did relative photometry, and you're relying on the lamp manufacturer telling you how much that lamp put out to then come up with your real numbers. Well, there's another way to do it. It's a little more intensive, but it's all we do now with LED. And you actually measure how much is there. And when you do that backtracking with zonal constants, you come up with the real lumens coming out of that source or that fixture or whatever it is you're looking at. All right. So relative photometry, what we used to have, now we have actual photometry, and we get a number like, okay, that fixture puts out 538 lumens. And there's no backtracking to the source or anything. So when we talk about last time, we talked about efficacy, efficiencies, and all those things. All we have to worry about now is the lumens we count, the watts going in, and you get some of those values, right? And you make a photometric report from that. All right, and here's an example. So this would be like an old school T8 fixture with a very good reflector on the top, right? Doing a lamp coming in and out of your page. The reflector kicking the light across the ceiling at these really big peaks. And then down below, letting what's left of that lamp come out through a series of louvers or something like that. So that you know when you get to the, okay, so this is an end view, like you slice through, and the white, what you're seeing, is a slice of those intensities, right? So you know that if you were at 90 degrees to the fixture, start at 0, come up to 90, and then you look back at it, there's no light there. But then as soon as you get above 90, there's a big peak coming out to wash across your ceiling called a bat wing, right? And then you come down below 90 and notice they've cut off the light above 45, so it's not very glary into the glare zone up around like 60, 70, 80 degrees. That's what the white is. And if you look at the other two lines there, you'll see a solid line, you'll see a dashed line. The dashed line is, instead of slicing through the fixture and looking at it endwise, you rotate around 90 degrees and you look at the fixture. And notice it doesn't have any of these big peaks or anything. Now it's just sort of a blob because now the light that's in there is just coming out. It's not being affected by any louver. Well, I guess the bottom might be, but or reflector or anything like that. And it's a way different distribution going in and out of the fixture if it were coming in and out of our page versus 90 degrees to the fixture, going across the page, right? So that's what those different things are. And then the 45-degree photometry is that solid line, and that's kind of halfway between. Now notice, every single one of those three lines merge at the 180 point, and they merge at the 0 point. So straight down, no matter where you go around the fixture, it has to be the same. Straight up, no matter where you go around the fixture, it has to be the same. And this is where sometimes your calculational program will say error, right? Because somehow that data got corrupted, and the plane of data at 0 or the plane of data at 180 didn't have all the same values in it. It can't not have all the same values in it. Because straight down is always straight down. Doesn't matter whether you're at 45 or 90 or 180 when you're looking in plan view, it's always straight down. And the same thing for straight up. Okay. So that's how those candle power charts are put into a graphical view so you can figure out that this is a great ceiling washer with some good downlight to it, right? Just by looking at it. And you don't have to go into your calculational program and do things and make a room and do all that stuff. You can look at this and you can figure out if it's going to be good for your, I'm only hanging my fixture a foot off the ceiling. I need the wide distributions I can get. Oh yeah, that looks good. And you can make a decision and move on. So being able to understand these is kind of important, right? It's a graphical representation of a big old chart. Any questions so far?
Bob, just really
Yes.
quick, you're on presenter mode, so we can see like the notes on the side. I don't know if
Really? Oh,
if you can switch
okay.
that.
I'm going to share a different screen maybe. Let's try that.
Okay, yeah.
Let's see here. Let's share. I don't even read the notes, by the way. Let's see here.
No, I know you were going off book for sure, but just
Well, let's try this one. Same thing?
it's loading. Yes, same thing.
Same thing. All right, so I'll try the other one. Let's see here. Let's stop share. Let's see if I can get to the other screen. Otherwise, I'll just unplug the damn other screen and we'll be all right, right? See, because that one seems like that should be it. All right. You know what? That's what I'm going to do. Do that. And then escape. Let's see. Okay, that's not working. What have I done? Do 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 do. End slideshow. Let's from. Oh, wait, no. Damn it. Escape. Current slide. Nope. All right. So I started that, but that you still don't see me, do you?
No.
All right. Let's see here. Tab. Zoom meeting. All right. So back to the Zoom meeting. Let's try share. And let's try that. And let's do from beginning. All right. How are we now?
It is still just showing all the admittance.
Really?
Yes.
Okay. Oh, what the hell? Let's see here. Let's go share.
Oh, something's happening. Okay. I can see your screen now.
And if I go from beginning, how about now?
That's full screen.
Sweet. All right, I'm gonna have to fast forward through a few things here. Oh, here we go. All right. So, any questions on
Is that
this?
okay? Thumbs up. Bueller.
Yep.
Anybody? Can you let me know if you can see
Anybody?
all right? Okay.
Looking great.
All right.
I did.
Thanks, Bob.
No problem. Any questions? If not, we'll move to the next one. All right. So here is a couple of views of, say, an outdoor fixture. Now, pay no attention to the red commentary because it's wrong. The blue is another slice through the side. So just like that last slide where we took a slice through the end view of a long fixture and we had those peaks going out left and right across the ceiling to give a good wash. Well, here, if we take a slice through where the maximum intensity is coming out of this fixture, you will see that there's a big old peak about 20 degrees below 90, right? That kicks out way in front or to the side, in this case, of the fixture. And then that ramps back, and then there's a fair amount of light coming up underneath it. That's what the blue one is. Now, if you were to rotate that blue one, let's see how to describe this, right? If you start at the very center and you were rotated 90 degrees down into the page, and then you swung that peak over so that the blue peak coincides with the red peak, right? The blue is in the cross section going through that. The red is actually a slice going around the distribution that's 20 degrees down from straight up, right? It's where the peak is, except now in plan view. So this particular fixture doesn't throw any light forward, really. But you get out to, what was that, 10, 20, 30, 40, 50, 60 degrees from straight out in front, and there's a huge peak running up that way. So this is like a roadway type 2 sort of fixture or something like that. There's a really super long, skinny distribution running up and down the page that we're looking at. And then the peak comes out to that same peak, right? The peaks coincide, just like straight up has to be 0, straight down has to match. Well, the peak of that blue matches the peak of that red. And if you were to draw a line from the center through the peak of the red, that would be the blue in plan view, right? And it goes both up the page and then down the page through those peaks. And that lets you know this is a very asymmetric, very long and skinny sort of distribution with a peak fairly high out so that you can throw light really far. Right? And that's looking again at what otherwise is a big old chart of numbers turned into a graph so that you can understand how this fixture works. And the slice through the maximum candle power, which is the peak of the red, looks like that blue. If you were to take that vertical slice from 0 through the peak of the red and look at it sideways, that's what the blue is. Everybody got that? Okay, it's not easy to understand sometimes, right? But that's more outdoor photometry interpretation from a graph. And the previous slide was more of an indoor representation of a fixture. Indoor fixtures tend to be a lot fuzzier, need a lot less detail. So a 0, 45, 90 representation of an interior fixture works well. But you can see how that wouldn't work very well for this particular fixture if you're looking in plan view and look at those reds, right? If you only did 0, 45, and 90, you'd be completely missing everything that this fixture is doing. So you have to test this fixture with a lot more angles, right? 0, 10, 15, 0, 5, 10, 15, 20, 25, all the way up to 90 to catch where those peaks happen in plan view. And then from straight down up to 90 again. So you have a much larger set of data for an outdoor fixture with optics like this than you do for the indoor. The indoor, you needed 3 planes of data. You needed 0, 45, and 90, and then those were mirrored all around the fixture. Outdoors, that's not necessarily the case, right? Look at how complicated this sucker is, right? Here's ways to get information out of your fixture that you can utilize, right? The integrating sphere counts lumens. Well, I do too, right? And the way that you use an integrating sphere is you have a source of known lumens. You throw it in the sphere and you take a view of the sphere wall somewhere with a luminance meter or what have you, right? You remove that known source, you put in your whatever it is, let it come to warmth and steadiness and take a shot of the same wall. And now you compare the two and you know how many lumens your other thing is that you just threw in there, right? And the integrating sphere integrates its output across the entire sphere. Now, you'll see some things referring to 4 pi. The hell is 4 pi, right? Well, that gets back to our definition of intensity. So in geometry, there's a thing called a steradian, right? And what a steradian describes is from a point running out into a cone, how much space that occupies, right? How big is that cone, right? And by definition, there are 4 pi of those suckers in a complete sphere. So there's 12 point, whatever 3.145 times 4 is, right? 12.4, 12.5 steradians in an entire sphere. And our definition of lighting, one of our definitions, is candela. And that's how many lumens are there in one of those 12 steradians. This is super important, right? So if you have a candle, that's where it came from. And let's say that candle emits light equally in all directions, and we ignore the amount of light coming down the base of the candle, right? So a source that is of 1 candela in all directions emits 12 pi lumens by definition, or 4 pi lumens by definition. So about 12 lumens. 1 candela evenly distributed into our 4 pi gives you 12 lumens, or 12.5, whatever it is, right? Because it's lumens per steradian is a candela. And candelas are given to us in charts of intensity in our photometric reports and things. And those can tell you how to then calculate illuminance far away, how bright the fixture is when you come back to how big the fixture is and how many candela it's emitting, right? You incorporate both of those things to tell you how luminous the fixture is now, right? And that's how all these things are tied together. I don't have a good graphic of that. I should have pulled that out of a book I have, but I didn't. So, but remember, one candela into these 4 pi steradians, 12 something, is 12 lumens. Now you start to shape that reflectors and things, and all of it changes. But there's kind of the way that it goes back and forth there. All right, and then here's our actual photometric report, and things here include how many lumens the fixture put out, what color temperature it was. That's the radiosity kind of stuff. Where was it across the color spectrum, right? How much power it consumed. That gives you all the things like efficacy, how many lumens per watt you get, all that kind of stuff, including here, a color analysis. Sometimes the color analysis doesn't happen or it's not paid for, and they just want to know the photometry information or how the radiosity interacts with people and the lumens and all of our definitions into a form that we can use in our programs to calculate stuff, right? So there's that chart, right? Notice the big chart in the middle, right? That's your candela chart, and it goes through all these different angles, 0, 22, 45, right? That means it's going all the way around the fixture in 22-degree increments. That's the top side of that middle chart. And then the other side of that middle chart starts at 0, and that's straight down. That's nadir, right? And it goes in increments all the way to 180 degrees, which is straight up. 180 degrees, also called zenith, right? So we've got a lot of data here for a fixture. Now you look over on the left side, it's a pretty simple fixture. They probably didn't need to do that much, right? It's diffuse. You're seeing a slice through one direction of it, and I would submit to you that the slices through many other directions are pretty darn similar. If I zoomed in on that chart, I bet you wouldn't see a lot of change running across those horizontal lines, right? It's pretty much the same no matter which direction you look at it. You then take into account those candela values and the reported luminous aperture of the fixture, and you take candelas divided by that apparent area, and you get luminance in candela per meter squared typically. Now that's important because there are a lot of guidelines nowadays, like WELL or the IES's RPs for office lighting and things like that, that tell you that you should be limiting your luminance at certain angles that are inherent to glare. So you get above, say, 65 degrees, you don't want to have a lot of luminance. So where are your luminance values in candela per square meter when you get up into that 60, 70, 80, 90 range? Now, if you have the same candela at 80 degrees and you have a 2-inch downlight shooting it out versus you have that same candela at 80 degrees and you got a 2-foot by 2-foot square putting it out, it's a world of difference on what the luminance is out of that fixture, right? Because you're dividing the luminance by the area. So the luminance of a 2-inch downlight, right, versus the luminance of a 2-foot by 2-foot square is going to be a huge difference. And we could do the math, you could figure it out, but you get the idea, right? So candela is independent of the size of the source, and it goes forever. And you can use it to calculate foot candles coming from that fixture and all that. But the luminance, how bright that fixture is, depends on how big that aperture is that's developing that candela, right? And that's the relationship then between candela and luminance. How big is the fixture for the same candela? Smaller the fixture, the higher the luminance. And there are restrictions on those things when you're sitting in an open office because you don't want big glare sources coming across the room at you. But it makes a world of difference if you're lighting that office with downlights versus 2x2s as to what's allowed, right? So think about that. And here's more charts for us, right? That we go back to that same interior fixture where we've got 0, 22, 45, 67, and 90. So we got a quarter of when you stare down at the top. And then it's quadrilaterally symmetrical. So then we don't need to test 135, and up to 180 and then to 270 and then all the way back around to 360, right? It's quadrilaterally symmetrical. So we only need that first 90 degrees in plan view. And then we talk about, when I talked about limiting glare and things like that, look at the top green box, right? Above 45 degrees, how rapidly are we dropping off to limit glare? And from the picture on the left, we're doing a really good job, And then in the numbers on the right, it sort of proves it, right? So the numbers on the right basically made that chart on the left. And then you can look up where the peaks are up above, and that's the second green box. Showing you that you have a peak candle power at about, let's see, where we hit the peak at 115 degrees. So 25 degrees above 90 is where we hit our ultimate peak in the 90-degree zone. So go across horizontal angles to 90, drop down the list to the biggest number you can find, and you find it at 115. And that's fantastic for doing an even ceiling wash when you get your peak candle power way out there. Lots of light fixtures, instead of this nice batwing on the top here, have a big old circle because it's just diffuse light, which is fine. You put a lot of uplight and that bounces off the ceiling and it fills the room, and that's fantastic, but it's not going to be the perfect uniformity ceiling that you thought you were going to get if you were using this fixture and the one with just the fuzzy uplight came into place. It's going to be a little more stripy looking on the ceiling, right? Because you don't get that throw out to the side. You do get more throw straight up. All right, we talked about luminance. So then you take those numbers, you divide the candela, which is lumens per steradian, by the apparent area of the fixture at that angle, and you get candela per square, whatever it is. In this case, candela per square meter. And when you look at those vertical angles and the horizontal angles, notice 90 it's brighter than 0. So at the end of the fixture is less bright than out the side. That seems pretty apparent from looking at the chart or looking at the graph, right? And then does it fall underneath the allowed values for whatever system it is that you're trying to check a box on? Whether that be lead or RP1 or whatever it is you're taking a gander at. And that will tell you if this is going to be a good fixture for you or not. All right. Next. This is just a different version of the same thing, a little bit less challenging on the candela chart. Remember that last one? Look at that one, right? The middle candela chart. Look at how much data there is there. Look at this candela chart, number 2. What is it? Number 3. Whatever. Number 2, the angle, mean, candle power, and lumens, right? Only one column this time. Why? Because it's a downlight and it's completely symmetric. So no matter which angle you go at in plan view, it's the same value. So you don't need all those other numbers, right? So depending on the fixture it is, you'll get more or less data in a lot of cases as well. This is all you need for a downlight that's symmetric all the way around. Just one value, or one number, from straight down all the way up to 90. Notice this particular fixture drops off. It says it supposedly has no light by 55 degrees. That's impressive. I don't know how they did that. But there she is. And then other things that you find on a photometric report when it's put out can include things like number 4, where you find out straight below a fixture how many foot candles there are depending on how far away you are. And that's a very simple application of a formula that we're going to go over here shortly, right? Adjustment factors, right? Notice I talked to earlier when in fact, I started the day off telling you how things were going to look if you changed color temperatures relative to base, right? And you'll see, although they're hidden for me right now because I just have something over there, you'll see there are different adjustment factors depending on which number you go to, right? And then this coefficient of utilization table, this is a super amazing, useful value in determining averages in a room by hand. And there's a lot of depth to using your coefficient of utilization. And we'll go into a little bit of that too. But that's all developed by taking a fixture into a lab, running it through the test, and then spitting out this stuff. Questions? All right, good. All right. Back here, somewhere along here. Aha, lower left side, number 3, you will see spacing crit, short for criteria. It says 1.2. What does that mean? That means that if you place these fixtures 1.2 times apart, that they are above wherever you're measuring your foot candles, you have a good shot at having even uniformity across whatever that surface was, be it floor, desk, standing desk, lab bench, whatever the hell it is, right? So 1.2 times. So if you were 10 feet above the surface you're trying to light, you could go up to 12 feet on center. and have a good shot at having even uniformity from straight below the fixture to straight in between the fixture. Right, depending on its shape of its candela and stuff, it might or might not be perfectly uniform, but it gives it a good shot. So when we look at this here and you look at these examples, right, it tells you the spacing criteria at this one, 1.1. And we talk about only being 5.5 feet up on the left over a desk surface or something like that. That means 1.1 times 5.5 feet, right? It's 5.5. They say approximately 6 feet. I wish they would just tell you whatever it is. 6.05 or whatever 5.5 times 1.1 is. Okay. So if you put those on that many centers, then that will have a fairly even uniformity. Now, how many foot candles there are depends entirely on how much light that fixture is putting out, and that's not addressed here. You can have the same fixture at many outputs of light to give you that quote uniform light, and you could put them at 30, 20, or 10 foot candles depending on where you ran up and down the dimmer. Right. So we're not talking about absolute values yet. We're just talking about the uniformity of those values. Right? Same fixture, instead of counting it on the desk, you count it on the floor, right? 8 times 1.1 is 8.8. We should have just put that on there. 8.8 would be the spacing apart to give you pretty uniform values. So, you could easily go 9. And in a hallway, do you need uniformity? Maybe, maybe not. Maybe you could go 10, 11, 12, and you don't care if it falls a little in between. But that's what spacing criteria means, is it gives you a shot at figuring out how far apart you can put the fixtures to keep things fairly even. Right? Beam. Beam and field. Beam and field are more used in floodlighting or reflectorized lamps than they are for just generic fixtures. Okay. So typically it's something used when you're track heads, right? Directional lighting, sports lights, things like that. You have usable things. So when we talk about beam and field, right? Beam angle, basically think of it as the usable light, right? So from 100% of your light in terms of candela, or intensity, out to 50% of that same value to the side, and then double it, right? Because it has to go to each side. So if you got a round sports lighter and you got a peak intensity and you come out to 50% of that intensity to one side and it's 20 degrees, well, times 2, that means you have a 40-degree beam angle. So 40 degrees of beam is pretty useful from 100 to 50%. Now, they also describe what's called a field angle. And it's very interesting, the difference in how those values relate to each other between legacy sources and now, right? So for instance, in a legacy source, in an HID sports light, you would take all the light behind the lamp, you'd shape it into a beam, you'd send it down to the field, right? And you would have a peak intensity out to 50 of X degrees. Well, where's 10% of that? 10% of that somewhere way out to the side where you can just see into the bare lamp, maybe. So you can have this super peaky something that drops down to a shoulder that then comes out way far. And you could have a, I don't know, 20, 30, 40-degree beam angle, but then have an 80-degree field angle. So what did that field angle tell you? What is that number? What's its value? It tells you how far a field you can basically see the light source is how you want to do it, right? I didn't mean to do that yet. So beam angle usable, field angle, where can you see it? When you get into nice regress light sources that are fairly tight, you're going to find that those numbers come very close together, where you come out to 50 and then drop off to nothing. Where you have a very exposed source at the edge of the faceplate of the whatever, you'll have a beam angle that goes to something, but then the field angle can be quite wider. And it's the beam angle that's used to define like ANSI flood types. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's the field angle that can describe those. And so sometimes they're not accurate for what the fixture is. My same example, very peaky beam in the middle, but then a flat shoulder, is not described well in ANSI because they count out to the shoulders. So if it gives it a 6, right, because the shoulders are so far apart, when the beam, if you just looked at that, it would give it a 2. It's really a spotlight with a bunch of fuzz, but you can't tell that by looking at just the field angle number, or it's a NEMA is what I'm talking about, the NEMA distribution, right? A NEMA 6 can be a floodlight if it's flat. A NEMA 6 can be a spotlight in the middle and a bunch of spare light if it's not. So you can't just judge by those values. Now, when you get into the tighter range, NEMA's 1 and 2, Well, there's not room for anything to be much different. So it's one of those situations where it's a very tight spot and it's got a very short shoulder. So those numbers can be useful, the beam especially. The field can tell you some things about the fixture itself that you might not learn from the beam. All right, so that's what beam angle and field angle are if you run across those things. Beam's the important one, 50 to 50%. Field is maybe more views into the fixture, right? You see a slice of a candela chart on the left, but you see the actual effect on the right, and it's not the same, is it? You don't see a dip in the middle per se, but you see how it's interacting with the wall surface at the distance you are away and the angles that you're hitting, right? So you can look at these things, you can understand how the light comes out, but then you also have to understand how it interacts with the surfaces in the space. This is a newer item, and it relates entirely to color. So if color is an important part of your application, you're doing a retail space or a car dealership or things like that, this becomes much more important than say office work or whatever, right? And we have a system called Color Rendering Index, which you may have been over already, and it relates things under 5,500 degrees Kelvin to like a black body radiator, right? And 100 CRI is matching that thing as it heats up. We talked about that last time for color temperatures, right? Well, you get off of 100, well, that means that you're not quite perfect. You're not matching it, but where and how? CRI is an average. What this does, this TM30, is it breaks it down into 16 different colors. And it breaks it down into a visual gamut to see how far away from the source comparison your source is. And they used a terrible example here because this thing doesn't differ much, right? But the red versus the black in that middle color, right? The farther you are away from the full black circle, the less pure you are to its color. And the more you are shifted into things like, say, that upper left quadrant. If our red line came out in zone 7 and 6 a little bit further, the light might start to look a little green. And you can tell that from this chart, right? And you can tell how well it's doing color fidelity by number 6. Looking across the line there, it's a really good source. And you can tell it's a really good source by looking back at the plan view of that chart that it never differentiates much from the reference source, right? The color chart on the far left is a little more off, right? Look how it does shove into the green, the red line does. And it does shove away from the red on the right. It does shove away from the blue on the left. So that source is not as good at adhering to perfect color as the one in the middle. And you can see that by that color chart then across all the values, right? It's got 80s, 90s, even down to a 70 somewhere, whereas our other middle one all stays up like in the 90s all the way across. So this is a great way to look at color if it's important to you. And if you saw a lot more red Ferraris, you want to make sure that you're not weak in red with the source you're using, right? You want to make sure of that. All right, now we get into cool stuff like calculating. So using those photometric reports, they put them into a electronic format, right? With a .IES at the end of it so that lighting programs understand that they can grab those values. Those are the candle power charts we saw. And then they can interpret them along with the room geometry that you build and work your calculations for you, right? So talked about calculating averages, the coefficient of utilization, super important to that. Lots of utility programs are written using that information so you can get a good, quick estimate of how many average foot candles you'll have in your space when you throw in, X number of these fixtures. Right? Then you can also do that same kind of thing manually with a particular fixture, its candle power chart, and the geometry to the point you want to calculate at. How far away are you and at what angles are you in both plan view and side view or vertical, right? And then there's computers that handle a lot of that stuff for us now, so we don't have to do anything by hand anymore. Okay. All right, lumen method stuff. Now this is where I may screw us all up completely because I want to stop sharing real quick. And then I want to go to video. Oh, wait, turn on. All right, you can see me. Let's see here. Is that actually visible to you guys? All right, cool. It's a little washed out on my little tiny thing here. Uh, so trigonometry lessons, everybody. Here we go. Back to school, right? Trigonometry, sine, cosine, tangent. These are super important when it comes to doing these hand calcs and understanding how light drops off relative to the surface that you're lighting it on. Okay. And other things to understand besides sine, cosine, tangent then are the relationships in 90-degree triangles. I do this by hand. Most other people would draw it up and have a computer thing for you, right? But when you get into 90-degree triangles, the relationship between 45-degree, right, and 30, 60, 90, the values associated with that, and then how the triangle works with sides A, B, and C on a 90-degree triangle, where A squared plus B squared equals C squared, right? So with those little bits of information, you can do a lot of work. And then finally, down at the bottom, right, if we have parallel planes and you have a line at an angle between those parallel planes, and you draw a right angle at each of those parallel planes, the opposite interior angles are equal. Now, this is important to take away a little bit of the complications that they throw at you here in a second. Okay. Um, let's see. Do I need to go back to that screen? Okay, are we back to the screen you guys see? Cool. Right. So it becomes very important, those relationships with each other, the opposite interior angles, sine, cosine, theta. Sine is your opposite over your hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent on those 90-degree triangles, right? Because notice we're using the cosine value here for our calculations. So you got to understand relationships and cosines really well. Now, if I remember right, again, it's covered up on my screen, but they did a little bad job of putting theta in over at the bottom of this particular one. It's that concept that I showed you on the hand-drawn thing of opposite interior angles, right? From straight down at the fixture out to where you're aiming, come down to the surface, come straight back up, and the two angles are equal to each other, even though they didn't put the symbol in the right spot there, right? And so that's called the incident angle, right? Incident angle and the cosine to that incident angle, right? So E is illuminance. Strange that it's E, not I, right? But that's the way it works. I is intensity in candela, right? We've been talking about all these candelas, which were lumens per steradian, so we understand it goes forever. And another comment on that, right? Since you're dumping lumens into a cone, you have the same number of lumens no matter how far away you get in that cone. So if you start taking slices farther and farther out in that cone, and you do the illuminance calc, how many lumens per unit area do you have? The area keeps getting bigger, but the lumens keep staying the same as you slice that cone farther and farther out, right? And so that's why there's less light farther away from a source than there is close up when you talk about foot candles. Same lumens into that cone, different slices have different areas. Farther away the slice, bigger the area, lower the foot candles, right? So intensity, candela, divided by the distance between the source and the thing you're measuring, that accounts for that spreading out, right? Times the incident angle, this cosine. Let me see. And that sort of describes all that stuff. Here they give you the cheat sheet for what I just talked about. And they already did some values for you for cosine and sine. And one of the things you can see is how this cosine starts to drop off, right? Let's move that one. And I'm going, okay, so notice on the cosine, back on our previous slide, if we aim that fixture straight down, the angle would be 0, right? And if you look at the cosine of 0, the value is 1. So in this calculation equation here, that value of cosine goes to 1. Right? So it's not less than 0. That cosine value starts at 1 and drops, depending on at what angle you start to hit at, right? So when we look at how the cosine starts to drop, notice straight down is 1. You go 30 degrees away, you drop 14%. You go 45 degrees away from straight down, you're now down 30%. But you're 45 degrees into going up to 90, right? So when you're down one, call it mounting height, and you're over one mounting height, your cosine angle has gone from, or your cosine value in that equation has gone from 1 to 0.707, right? You keep going farther and farther away, and that cosine value drops. Notice you lose 30% in the first 45, but that means you lose 70% in the next 45, right? It's something you might not have thought about, right? The first 45 doesn't matter near as much as the second 45 in terms of how much you're going to reduce the foot candles you're calculating at that point just by the cosine part, much less the distance squared. So you can see how rapidly illuminance drops off as you move away from things, even if you have a source of uniform candela. Let's say it was the candle we talked about to start with, right? It had an intensity of 1. Well, you start going out to 45 degrees away, you are now 1.4 times on a D, square that, you're about 2 plus for your D component. And then your cosine's gone down to 0.707. So you divide it by half, times it by 0.707, and by the time you get, a foot away, you've dropped however many percent from what it was straight below. Right? That's how these things interact with each other. Sine, that's confusion is what they try to do here. But cosine, sine opposite over hypotenuse, so cosine adjacent ka, toa tangent opposite over adjacent. So if you have two sides of these triangles that you're looking at for your geometry, and you have a calculational engine at your hands, which I have an old TI 30 solar, but if you have an iPhone and you turn it sideways when you're in calculator, guess what? You get tangents, cosines, and sines, and you can do the inverse of them too. So you can start to figure out these numbers really easy, right? Let's see here. Angle of attack, right? It's an incident angle is what it is, right? So from straight up to your surface over to the line to the fixture is called your incident angle. Now, this is where they try to confuse you a little bit. They give you a sneaky way to use the same angle and use its sine or something. I prefer not to confuse you guys. I want you to always think about an incident angle, and I want you to look over here on the left-hand side of this particular deal, and I want you to be able to figure out that the incident angle is what they're now calling alpha in this particular case, right? Instead of messing around and switching things from cosine to sine, which they advocate doing here, I say always keep counting your incident angle, and you can use that opposite interior angles and or the thing where all three angles in a 90-degree triangle, add up to 180. And you can figure out that incident angle and worry about its cosine instead of other values. So if you see me not paying attention to the sine thing, it's deliberate. We've already talked about a lot of this. Number 3 is the case where our cosine value is 1, right? Number 2, now instead of the candela coming straight down from that lamp, we have to figure out how many candela are coming out at that theta angle. And then that theta angle is also equal to the incident angle hitting the ground. So we'll have a cosine value of that. We'll have a D that's bigger than the D on number 3. Number 2 is, right? And then we're going to have to go into the candle power charts for that lamp and figure out how many candela are coming out at that angle theta, whatever it is. Run all those things into the formula, and voila, you have how many foot candles are hitting at that little orange spot. Now you come back to number 1, and it's the straight out candle power from that fixture, or whatever its nadir candle power was, because we're aiming it at the spot. Now we don't have to interpret the chart anymore. We just have to get the straight out candle power. We still have an opposite interior angle of theta. So we still have that cosine number, and we still have that D. It's just a question of which candle power number do we pull out, number 1 versus number 2. Number 1 is your center beam candle power, they call it a lot. Number 2 is then how far away from center beam, call it 30 degrees in this case. What is the intensity at 30 that we now use for that I value instead of the straight out? Using the straight out again at number 3, now we don't have any cosine to worry about because it's straight away. Does everybody get that? Okay, good, because some of these are a little confusing. All right, now I can't see what the hell's going on over here. Hey, move it out of the way. Here we go. All right, good. So for this guy, right? Straight down. That means our cosine value is 1. Pretty easy, right? So if we go back to cosine value of 1, 7 foot and 3,000 candle power. Look at the lower left one over here. 3,000 candle power, 3,000 divided by 7 squared times 1. What's the answer? Who's got a calculator? 3,000 divided by 49. Let's see. 2 per 100. Should be like 60 something, right? Anybody?
61.2.
Thank you. Thank you very much, right? So see how that works. 3,000 candle power. Cosine means 1 because we're straight above the damn thing, and divided by d squared. Now, this can be super handy. Just this one little calculation thing right here. We've got a lot of municipalities around town that say, thou shalt not go over X foot candles outside. Well, if you look at a photometric report of the wall pack you want to put up, now this is not always true, but let's say it's a flat glass one. Usually your maximum is going to happen right below the fixture. It can happen otherwise, but let's say it does. You can look at that straight down candle power, look at where you're going to mount it, do the math, and say, am I going to be over that municipality's max? Right? Boulder doesn't allow more than 5 foot candles. When I used to use compact fluorescent downlights, they had a pretty intense punch down below, and I had to take even the smallest one up to like 12 feet to get below 5 foot candles. But I could do it all pretty easy because I understood my little formula, right? I didn't have to get into a program and start calculating and doing all that crap. I could just look, do a quick calc, and say, hey, my max is too high. So very handy to know these formula and things about them. Right, here we go. Now, this one was, I was going through this today. I'm like, oh, you guys are really trying to confuse people. We come back to the concept of beam. Remember that from a few slides ago? So we had an intensity straight down was your max. The beam happened to be at 30 degrees out. And we defined beam as 50% of max candle power. So we had 3,000 candle power here. We're calling it a floodlight because we're going to talk about its beam, right? Its beam happens at 1,500 candela, and that's 30 degrees away. So now our formulae, right? The I becomes 1,500. The D becomes 8 squared. And the cosine value by our alternate interior angles, right, is cosine of 30, which is 0.866. So now the calculation would be 1,500 times 0.866 divided by 8 squared. Anybody? Who's got that calculator? 1,500 is the I times 0.866 divided by 64.
Uh, 20.29, I believe.
There you go, right? So now we have 20 foot candles over there. We calculated what, 40 or something? I forget what it was, but straight down from this fixture. So if it's got a beam of 30 degrees to the side, that means its full beam angle is 60. So that's how the beam angle would be described with this particular floodlight. We don't typically take into account beam angles and such interior, which is why this is a little disingenuous, right? But we're at a floodlight outside. These would be things we talk about. Then if you took that fixture and you aimed it at that spot instead of aiming it straight down, right? Now the I goes to 3,000 in that last number instead of 1,500. Everything else remains the same. And so instead of 20, we'd have 40. Because we aimed the fixture over to that point and we doubled the candle power coming out towards that point. Okay. And then I don't know what that one was. I don't know why they changed it to 1,500 here. Again, some of these illustrations get a little weird. All right, now, this is where they want you to go and start to use the sine angle because now we're doing verticals. Well, I submit to you, don't worry about switching your brain around too much, right? So, for instance, here, if we do the opposite interior angle, you notice where the 30 degrees is. That means the 30 be on the other side. We know that in a right triangle, those two values of the 30 plus the other one should add up to 90. So that means our incident angle is 60. So now instead of using sine of 30, I would use the cosine of 60. Stay with cosines the whole way and not worry my brain about this switcherooski. And you can do the same kind of math that we were just going through. Now counting that incident angle is straight out from the wall out to where the fixture is aiming at it. And now that's a 60-degree angle in this case, right? We did the opposite interiors. We know that 30 plus whatever adds to 90, that whatever is 60. Now we use the cosine again. We never get into sine. It was a sneaky trick to avoid having to do that extra step, but I always do the extra step because it works better for my brain. If you can get the sine version, please go ahead. Right? This is how I explain. Right? And we just we go through these things again and again. Right? Now, what this one is, this little table over here again. Right? This is them now doing calcs for you ahead of time. So they take the intensity value straight down. And like in this spot version, notice you have Ds of 5, 7.5, 10, and 12.5. So they have that intensity value straight down, and they now divide that number by 25, whatever 7.5 squared is, 100, and whatever 12.5 squared is. And then they get the foot candles at the middle of that circle that far away. You could backtrack and find out what that candela value is there. You look over the left-hand side, well, there it is actually in print. Either way, you could come back and figure those things out. Oops. Then, right, they start to give you L and W, and those are out to say the 50% numbers, like this beam angle that we talked about. So how big is the, quote, circle of light? Now, imagine it doesn't just perfectly even across to the edge and drop. It's warmer in the, or hotter in the middle, right? Higher foot candle number, out to wherever the hell 50% happens at whatever number that happens to be on the ground. And they tell you the length and width of that area or that circle out to where 50% hits the ground. There's still light past that. It doesn't just die. But they give you an idea. So if you were to take that spotlight and put it 10 feet above the floor, they're telling you that the 50% number hits a circle 2.6 feet wide. So if you put those 10 foot on center, do you think you're going to have a uniform hallway? No. Not if the, quote, circle of light was only 2.6 feet across. Even with some bleed, you put them 10 feet apart and there's going to be dark spots in the middle. So what if you went to the very narrow flood at 10 feet? Well, now it's a 3-foot circle. Not that much different. You go to the narrow flood on this fixture, now you're at least out to a 4-foot circle. But still, if you try to put them 10 feet apart, you're going to have some uniformity problems. So this particular fixture in those numbers might not be a great hallway fixture, but it might be a great fixture for highlighting a flower arrangement on a table. You come back up to 5 foot with this dude. You're on a table in a low ceiling, and the spotlight will put 600 foot candles on your flower arrangement. Oh, that'll make it pop, don't you think? Right, so you can use these things to then give you some information. If you were to take that fixture and aim it at a wall, right over at 60 degrees, it'll tell you now different numbers for the circle that hits the wall. And there are a lot of these charts included in things like track lights. Right, so if you aim the track light up, or adjustable downlights, if you aim the adjustable downlight up, they can make a chart for you like this, so you don't have to go do it yourself. And you might be able to, you know, tell something from these charts about how to use the fixture, right? Pre-done calcs for you, so you don't have to. All right, so that was the, all right, that was the point method, right? And we talk about distances, intensities, cosine angles, all that kind of cool stuff, typically done at a point from a fixture or maybe a few fixtures around a site. We used to do that, right? You'd find wherever you thought the farthest point away from 2 light sources were, dive into the geometry of the thing, figure out what the candela were hitting that point from those 2 light sources, calculate the foot candles from each, add them together, and you know your darkest spot was some number. And then the outdoor fixtures also had a coefficient of utilization for their street side and house side. If it was all perimeter fixtures, you'd take the coefficient of utilization of the street side times the lumens of the lamp divided by the area of the site, and you'd get an average. You do your darkest point by hand, and now you would have an average to minimum. And that's why a lot of IES recommendations have put out in average to min, because that's how we used to calculate. Now, some things have changed, and they'll give you recommendations in max to min, like garages nowadays. They'll give you a recommended 10-to-1 max to min. And again, you could do that by hand. Maximum's probably underneath a fixture, depending on its distribution. And again, go find the darkest place, and maybe you could do it by hand. But we have programs that then do these things again and again and again for you at every single point, and you can look at them that way. Okay. The lumen method, right? This is what I just sort of alluded to outdoors, where you get this coefficient of utilization. And then you count the lumens in the lamps. You count the fixtures in the room. You use this coefficient of utilization, which is based on the room characteristics, and you can come up with an average. Okay. I mean, that's the simple way to do it. And they have to break it down into all of this because, again, differences between how far away you are and the geometry of your space really affect how light gets from the light fixtures down to the work plane. Think of a huge warehouse. You got a lot of lights. You got a huge area. The walls really don't mean squat, right? All the light from the fixtures make it to the work plane. Now, instead of a huge warehouse, think of a grain silo. And you put one light up at the top of the grain silo. How much light from that light makes it to the bottom? Not a hell of a lot, right? And this is what gets taken into account in this coefficient of utilization calculation, is to how the geometry of the space affects how much light makes it from the source to the work plane. And then that'll change depending on the distribution of the source. A spotlight in the silo will work a lot better than a floodlight in the silo, because the spotlight shines all the light, or at least it tries to, all the way down. Whereas the floodlight's going to hit a lot of the top of the silo, start bouncing around, and you're never going to see those lumens down at the work plane, right? So a little preview, right? You count the lumens. That's what I do, lumen counter. How many lumens are there total from the sources? The coefficient of utilization tells you how that fixture interacts with the room. You have to figure out light loss factors. We'll talk a little bit about that here, right? And then you divide it by the area, and you come up with an average. As opposed to these candela, things. Let's see here. One thing I wanted to discuss real quick that I skipped. I'm gonna go back. This cosine angle thing. All right, we're gonna try my hand done stuff again here. All right, video. You should have the video. All right, so I did a hand-drawn cosine right over there. And then on this side, we've got like a wall wash application where we have a fixture 18 inches off the wall and 10 feet above that wall, right? What I'm going to do to you now is I'm going to read you some numbers. So when we're 18 inches off the wall and we drop down to 18 inches below the ceiling, what angle are we at for incident, everybody? Even numbers, 45 degrees, right? So 45 degrees over. So already when we come down 18 inches off our 10-foot ceiling, we're at a cosine angle of 45, which is 0.707. We've already lost 30% of our light to the cosine, right? If we go down to 5 feet down the wall, let's see here. How do I do that? We're already down to 0.287, right? 5 feet down the wall, a foot and a half back. Our cosine of that angle, which is 73 degrees at that point, is down to 2. So we've lost 70% by the cosine when we're 5 foot down from our 10-foot ceiling. Not to mention the distance thing. We get down to the bottom of that wall. So you're trying to do a calculation for this wall washer, right? And we get down to the very bottom of that thing. We're 18 inches back. We're now 9 feet down, right? We're at an 80-degree angle now. Incident angle is 80. Cosine of 80 is 0.165. So we're at 16% in that cosine number in our calc, where it's I cos theta over d squared, and our d is huge. So this is why it's really hard with numbers to show how a wall is going to look very well, because walls are often very textured, and texture returns light to your eye differently than just a flat surface. So when you get down the wall with a grazer and you have texture, there's bits of that texture that face right back up into the light source and going to be a lot brighter. as opposed to a very smooth wall with no texture, where you're not going to have much of that return. Or if you have a shiny wall, even worse, where nothing's going to come back to your eyeball and you'll never see that you're grazing the wall anymore because the light's going to bounce off and down instead of coming back to your eyeball. But the actual calculation of even how much light hits the wall, you're down to, what did I say, 0.165, not to mention the d squared by the time you're 9 feet down from your wall washer. So the actual vertical foot candle numbers are going to look an awful lot like they're just super high at the top and super low at the bottom, and that may or may not be helpful to you. Sometimes when we're doing super tall walls, what I will do is I will take the meter of those grids, and instead of aiming them out from the wall where these cosines take over, I'll aim them back straight up the wall towards the source. And you can see that there's 50 horizontal foot candles down there, where when you turn that meter to the side with its 0.165 and his double thing, it shows 2. There's still a lot of light there. And if you have a textured surface, you're going to catch some of it. But it's not going to look like there's a hell of a lot when you do the calc because of these things, right? It's a really weird situation. So I wanted to make sure I shared that with you. Let's go back. See if I can get that going again. All right, are we back? Cool. So cosine angle. I want to just do a little bit more of that. All right, so now we get into calculating averages. Right? How much light leaves the fixtures? Here's our counting of lumens on the top, right? Divided by the area on the bottom. There are assumptions built into this model, right? It was all done with descriptive geometry and what's the word I'm looking for? Radiative transfer, right? And if your room is super long and skinny or something like that, it's not going to work so well. But with a length to width ratio less than 1.6 to 1, diffuse room surface reflectances, that's what it's all based on, a single fixture type spaced evenly, these things work out very well. And you'll find quick calculators on lots of different websites that utilize this way of doing things to give you a result. When you do a 30 by 30 classroom, you throw in 9 of the fixtures, you're thinking about what's your foot candle level. This is the way they do it. Okay. We talked about that already in reflection, dimensions, reflectance, distribution. We talked about in the silo, right? The spotlight versus the floodlight. The spotlight's going to be better. You can understand that, right? And here's the big coefficient of utilization chart. The way that this is read, right? The CU that goes into that lumen counting thing are all the values below. Your ceiling reflectance runs across the top. Your wall reflectances are the second line, right? And then your room cavity ratio is the thing going down the left side. The room cavity ratio is 5 times the height times the length plus the width divided by the length times the width. And I'm sure there's a graphic coming up here that shows you what that is. But you're looking at 0 and 1 being the warehouse I talked about. Long, big open area. Lots of light from the fish is going to make it to the work plane. When you get to room cavity ratio of 10, you're getting more towards the silo. And notice that value is dropping and dropping and dropping as you get taller and skinnier and skinnier and skinnier. And that's what room cavity ratios of 10 are. Tall, skinny rooms versus long, flat rooms. And in tall, skinny rooms, less light makes it to the floor, right? Now, in tall, skinny rooms, as you start to reduce your wall reflectance things, it even gets worse down below because you have to count on the light bouncing off the walls. So if you lower your wall reflectance, bad things happen in taller, skinnier rooms compared to shorter, wider rooms. Okay. So you lose, let's see how that works. In any case, that's how it works. You can see how it runs up and down the chart. And then for this particular fixture, the ceiling reflectance doesn't seem to make a lot of difference, but just a little as you run across the rooms, right? If you go from 30% ceiling reflectance to 80% ceiling reflectance across any of these particular lines, there is a difference. So the ceiling is affecting a little bit in the room, and you can kind of zen things out of this. Now, all of these CUs are based on a floor cavity reflectance of 20%. Well, what if that's not right? How do you modify these things? Well, what we did, I'm going to stop sharing there, and then I'm going to share. Let's see here if I can get to those angles. Oh, do I not have it open? Oh, there's our thing there. That wasn't it though. Let's see if we get to those. Oh, nope. Oh, here we go. Oh, I see what's happening. When I unplugged that, it killed it. Close that window, try again. Patience. Ah, now let's go. Okay. Share. Oh, no, that's not it. Share. We're having an issue here. Where did you go? I just had you. There we go. All right, so now that. Aha, I think I might have got it. All right, did we see that?
Yes.
Cool. All right, so what this table shows you is if you have a base reflectance of things other than 20%, how to modify based on room cavity ratio those charts. So you initially found your room cavity ratio. It was assumed 20% base. If you have a different than 20% base, you pull that value from your room cavity ratio, you multiply it by these values, and you can put it into those calculations, right? So there's ways with charts and things like that to be able to modify even the CU value that you get off of the photometric report to make sure that you can use it, okay? That's the thing that I wanted to make sure that we were at least getting through. All right, and let's see. All right, are we back to the presentation? Cool. All right, wanted to show you those things so you can modify even these charts if it's other than 20% base reflectance. So there's a bunch of chart searching and interpolation of what if you're at room cavity ratio 4.4? Well, you have to then figure out how far between 4 and 5 you are in any one of these charts. I had a fancy calculator. I even put a little program in way back when, and I could put in the values all around it, and it would spit out the interpretation between the four. It was super cool. Room cavity ratio. Oh, there we are. We're back to our silo versus not silo sort of a thing, right? We all understand that now. Ceiling cavities have something to do with it because you might have dropped luminaires. And again, there's modifications for those. Oh, and here's our room cavity ratio calc, right? So to get those numbers from 0 to 10 on the left side of those charts, you did this. What is the height of the cavity ratio? That means from your fixture to your work plane. The length and width of the room is a plus divided by the length of the room on the bottom. And that gives you that room cavity ratio going from 0 to 10. 10s being silos, 0s and 1s being long flat rooms. Okay. And some examples of how to calculate that. So in those charts, oh, where'd it go? There we go. In those charts, notice we have a lot of reflectance values floating around at the top, the ceiling, the walls, all that kind of stuff. Well, how do you determine that? Do you know what's in your room? We default to office spaces being 80-50-20, right? You can default an industrial or a warehouse space being like 50-30-10 or something like that. And you can dive into these fixtures. But if you maybe even know a little more, right? Notice we've got reflectance values here of all kinds of different stuff. Your architect will be specifying finishes in a space. And if you want to get accurate, you can even ask them, well, what, What colors are you painting the walls? You wouldn't believe how many times, well, you told us there'd be this much light there. It's dark. Well, send me a picture. Oh, well, you painted the walls forest green. That was not what we were counting on, right? I mean, you dropped a curtain of dark green behind the playing surface. How do you expect to have light bouncing off that wall come back to help you at the end line of your tennis court when you dropped a curtain there that you never told us about, right? So getting accurate modeling information and reflectance information can help you be more accurate in the foot candles that you predict, right? Notice on the right side, floor and furniture, wood light, really light wood is maybe 35% reflective. So if you're lighting your beautiful wood ceiling and you want it to be your primary light source, it's not very efficient, but it can be done. But understand that only a third of the light you hit it with is going to bounce off. And then how much of that's going to make it down to the floor? Might be a better idea to light your wood ceiling with something of much lower intensity to make the wood beautiful, and then light the space with something else. All depends on your aesthetic and how much energy you want to throw at your situation, that kind of thing, right? Brand new concrete, gray, right? 40%. Lots of people will try to use that in parking garages. Well, how long is that concrete gonna be brand new in a parking garage? For tires, tracks, and cars and all that other crap come through there. I don't tend to use reflectances in parking garages because I don't want to count on them. But you could. I had a design group recently want me to run calculations for a value engineering solution on a parking garage, and they wanted to use 30% for everything, and that's rational when it's brand new. Maybe not over time, but at least for a comparison purpose, you could compare the A fixture to the VE fixture with 30% reflectances side by side and determine if it's going to be, okay or not. Anything else I want to say on oh, indirect lighting, right? A lot of people do that in a lot of different scenarios. If it's a tile ceiling, you can go ahead and do 80%. Oh, did it again. If it's a white painted something else, it's going to be below 80. And it's a question of what's the something else? How much light trapping is going on with that something else? A lot of times, if I know something's being painted to white, I'll call it 65 instead of 80 and go forward with that. And maybe that'll account for all the light that gets trapped in between the ductwork and the spray-on insulation and whatever else was being painted white, right? Things to understand when you're doing either kinds of calculations, whether you're diving into these values in charts or whether you're doing a point by point in a program. Estimating the reflectances more accurately can give you a more accurate result. I have a friend who went into paint representation, and she gave me, I just have a little window of me somewhere. She gave me this color chart of paints, right? And you can go into these paints and you can look at the backside of these things and you can find out that soulful blue, one of those, has an LRV, light reflectance value of 21%. And that was, I'll put my middle finger at it. I'm not trying to be mean, right? That blue right there is only 20% reflective. So people tend to overestimate reflectance values. Don't overestimate reflectance values. They can give you false results. All righty. So diving into the values, pulling out the accurate CU number, right? Depending on room cavity ratios and reflectance values, you can take a lot of time getting to that CU number to plug back into the program to give you answers. Oh, in fact, here on the right-hand side of this particular slide, we've got our spotlight versus floodlight for that silo. And they've even shown you, 72 on the left circle, 88 on the right circle, both at the room cavity ratio of 9. It makes sense, right? A silo, taller, skinnier, a spotlight's going to put more light down than anything else. So, and right there, you can see that reflected, probably a bad word to use. You can see that in the numbers from 72 to 88. Okay. Same thing. We're talking about diving in. Ooh, here we go. Good deal. Light loss factors. So there are lots of things that go into predicting what your levels are going to be like in the future, as opposed to day one. right? Day one, you got a lot of initial values. Everything's clean in a brand new building. Nothing's depreciated. There's no bugs in your fixture. You can figure out what quote initial foot candles are going to be. Over time, though, things are going to depreciate. And how are they going to depreciate and how fast is what you have to decide as a designer. A lot of people tend to ignore many of these things and just talk about the first one. Light source lumen depreciation. How far down is my light source from beginning at some time in the future? And you have to determine that time to figure that out because all light sources depreciate differently. We used to kind of have standards for the standard light sources. Compact fluorescence did this fast, metal halide went that fast, HPS went that fast. Well, now you got quote LED. Doesn't even matter if it's the same chip. It could be built into 5 different things, the heat's sinking doing differently, and the depreciate's going to be different across all 5 of those things, even though it's the same damn chip. So you have to look on a fixture by fixture basis as to how they depreciate over time, and you will be given a value somewhere, somewhen, of a depreciation number, and people tend to gravitate towards that and use it. But there are other things to consider. Luminaire dirt depreciation. In an office, probably not going to be much. If you're in an office next to a rail yard or a major highway, right? Maybe your air filtration system is not so hot and your luminaires are going to get dirty. Maybe you're in a warehouse. Maybe you're in a foundry, right? Those are all different situations as to how over time your fixture is going to depreciate in output because of the dirt that deposits onto it. And the dirt that deposits onto it depends on how the fixture's made, right? If you have an open fixture where air flows through, it's harder for dirt to settle. If you have a closed fixture that's only indirect, when the dirt settles on the lens on top of it, that's really going to affect your output. If you have a lensed fixture that's only downlight, how much dirt really is going to get on the bottom and accrue. So there's a bunch of different charts you can go into to figure out how both your room surface and your luminaire are going to depreciate over time relative to the length of cleanings in between. And I think I've hashed up some of my stop sharing and going to the charts. So I'll just let you imagine that in your head, right? They come out of books. I've got images of them photocopied. But it talks about a very clean environment cleaned every 24 months gives you X value. A dirty environment cleaned every 12 months gives you X value, right? To plug into these things, to take into account over time of how things depreciate. Ambient temperature factor doesn't come into play much, although it was a bigger deal during fluorescent times because fluorescent lamps are very subjective to temperature as to how their outputs went. I think we might have talked about that in terms of T8s and T5s when we did sources. T5s were optimized for running inside a fixture at a higher temperature than the T8s did in open air, and it made them more efficient because they took into account the thermal factors and how they operated. So lamp luminaire depreciation, room surface dirt depreciation, luminaire dirt depreciation, some of those things you might want to throw in, especially if you think you're getting into a dirty environment. The other one that's not mentioned here, that if you were going into an old situation in fluorescent land, would be called the ballast factor. And the ballast factor is how that lamp, I think we talked about that last time, is how that lamp operates on a real ballast as opposed to the reference ballast back at the lab, right? Real ballast for T8 lamps kind of ran about 88% of their output. So that's something you would want to take into account in your calculations. Otherwise, you're missing out on, well, you're losing 12% of the light that you think you have if you didn't take that into account. So ballast factor could be added to these things in terms of values that you come up with for depreciation. And then the big key, again, we used to have a number for a fixture. It happened at 40% of rated life, so you could figure that out, right? Now you'll get a number somewhere down the road, and you have to figure out when you're going to do that calculation factor for. So how often are cleanings? When are you doing the calc for? At the end, before they get cleaned again? Right. Are you trying to match up to what the fluorescent lamp used to do or the metal halide used to do? The metal halide would burn out after 20,000 hours. It was down to half its output. Well, 20,000 hours into an LED, you might only be down to 95% of your output. Depends. So when are you doing this light loss calc for, and then come up with the appropriate numbers? not something people think about when. All right, examples, calculations. You know, you guys used to actually have to do a quiz and turn them in. You don't have to do that anymore. But you see where you start to plug the numbers into the formula. You dive into the room cavity ratio charts, you get the right number, you pull that back out here once you've calculated and gone in. You apply the light loss factors. And you use that thing to come up with an average. Still used in a lot of ways in a lot of quick calculation programs, just it's all hidden from you and you don't have to do it by hand, okay? Then we get to computers doing this stuff for you, and that's where you get into a lot more point-by-point calculations and then adding them all together. And then some of the programs can then try, and I say that, to then show you what it might look like when light bounces off of surfaces. Here's the problem, right? Computer screens can't have the same dynamic range that the real world does. So automatically they're a little suspect. What renderings do for you in a lot of ways that are really good is they help you understand the spatial relationships of places, but the lighting effects can or cannot be quite accurate, right? You can look at some situations where people have done renderings and taken photographs afterwards. And even the photograph, it's a little hard, right? Because you're not seeing it with your own eyeballs. It can be a useful tool to show people intended effects, but as far as actual representation of real life, it can be a little difficult because the modeling of the surface itself and how it reflects light is very complicated. There are luminaire design programs that take into account every single angle of incident light off a piece of reflector material and how it reflects in every other angle. I guarantee you that those investigations have not been done for the brick in this rendering, right? So it's assuming maybe a diffuse reflectance and a color. So take renderings of lighting effects with a grain of salt. They can be very useful, but they can also be very wrong because the representation of the materials and the way they reflect light might not necessarily go well. So very good spatial, sort of good to get the intent across, but not necessarily something that's going to be perfect and look just like it when you get to the site. Okay. This is one example of one of those simple programs I talked about that still do a lot of room cavity ratio stuff. One fixture on an even grid in a room defined with diffuse reflectances. And once you define all that stuff, you can plug in 30 for your foot candles. And up on the right-hand side, it'll tell you need 16 of them. And it'll tell you the spacing, right? And notice some of these programs, they give you a good idea of how many fixtures there are, but look at the spacing this program came up with. It says 5 foot by 5 foot for this room, for the solution. Have you ever put in 2x2s on a 5 foot by 5 foot? No, because your ceiling grid's in increments of 2 feet. So you know that with this particular, so what this program does for you though, is it tells you that for this particular fixture, for this particular room, to get 29 foot candles, you need 16 of them. Well, you go in and figure out the best spacing for those 16, right? Based on your ceiling grid and all the rest. And maybe instead of 16, you need 20 to make it look right. Or maybe instead of 16, you only 9 are going to work. And instead of, this fixture doesn't tell you the fixture. Instead of whatever fixture it was, now you go to a fixture that's got 1.5 times that output and makes it work right. So it gives you good feedback. It doesn't necessarily give you the answer. Right? Sometimes that answer will come back at 4.86 by 3.95 feet. And again, you're never going to put a fixture in that way. So it gives you useful feedback that you then, as the designer or engineer or architect or whoever, can utilize that to give you a right answer, and you can come up with something pretty quick. Then we get into ray tracing, lots of calculations and renderings, and all these things in the rendering to the right, like somebody spent a lot of time to build those chairs. Do you know what color the chair is? Do you know what fabric is going on the chair? I mean, think of how detailed you and how much time you could spend creating something like this. I work at a lighting agency. My average time on a job is 2 hours. I do not make renderings. I don't have the time. I don't know the project. I don't know the furniture. But if you're on the design team and you're the interior designer and you want to show off your beautiful chair fabric, right? Maybe that's a person who's going to get into doing a rendering with the chair fabric perfectly. They're going to do it in Revit. It's going to look wonderful, but then Revit doesn't have a good lighting engine. So it comes back to us to then calculate, well, is there enough light then to fill that beautiful red chaired space with the amount of foot candles you need? And you can get into a lot of depth that way. Point by point analysis is what I talk about them doing for you. Calculational engines where they count not only the direct illuminance coming out of the fixture, but they count the bounces around the room and bring it back to points. You can use ISO illuminance lines like you see here in blue and green and light blue and black to show you contours, but they don't necessarily tell you what looks so much brighter than something else because of the way our eye brain system works. That's the other issue I have with people doing the same representation in the color scheme of like red, blue, background, where red is the hot spot and yellow is the lowest. Well, if you do that red to yellow over 10-foot candles instead of 100 and they still look red to yellow, what's it telling you? I guess there's some information there. Yellow is going to be less than red, but does it look that different? I would submit to you if yellow and red across a 10-foot candle scale at 50, you're not going to tell the difference, but yet there's that yellow red thing going on. Whereas yellow red, where it's 100, where it's red and 10 at yellow, by God, yes, you're going to notice hot spots. But it's all relative as to how you set that scale of those things. So how useful are they? They can be if you understand what you're representing. Okay. Again, different ways to do calculations and renderings. Somebody had a pattern for the, whatever those are, blinds over on the right-hand side that make it look really cool. How are you coming up with that? I don't know. Did you apply a pattern to a reflectance? How did you build those? How much time did it take? Again, where do you sit? How much value are they to you? And how much do they represent the real world? Those are all things that you have to kind of blend. Okay, so lumen method. We counted sources and lumens, coefficients of utilization, which were based on room reflectances and geometry, and we came up with averages. Pretty simple. Detailed analysis, programs. They take into account that entire candela chart, positions in the room, geometries, and they do a whole bunch of calculations that would take us way too long to do by hand and can be very much more accurate then. Because you can examine vertical surfaces in the room, right? The ceiling. Remember that batwing fixture we had? Well, if you had a batwing fixture from way long ago in our program, you had them spaced out perfectly on centers, and they were doing this beautiful job on the ceiling, and that was important to you because you wanted to see a beautiful job on the ceiling. And a fixture got proposed that only had just a regular diffuse distribution on top. And now it's going to be two stripes of light over your fixture. Well, being able to calculate that ceiling plane is pretty handy then, right? So you can see that instead of a 5-to-1 uniformity from fixture to low spot to fixture, now it's 20-to-1. Fixture to low spot to fixture. Now, instead of a beautiful uniform ceiling, you have stripes. Stripes are still better than nothing. But you can tell that by doing the calculations. And in the calculational programs, you can pick which surface you're going to put the calcs on, and you can take a look at those things. Getting it out of the program to show to people is a little different, but it can be handled. All right. Now, I get a lot of people who come to me and say, oh, the city told us we have to do a calculation of the existing lighting. Even if you knew the model numbers of the fixtures that were out there, even if you could get a hold of IES files from 18 years ago for the fixtures that are out there, and even if you, I guess the only thing you could possibly get to is if you knew that they had been recently relamped, reballasted, and cleaned, you might be able to come up with something accurate. Other than that, it's a crapshoot. And if you're in a position where you have to stamp a drawing on a crapshoot, you might not be comfortable doing that. So this is where field measurements come into play. And if it's that important, right? Doing a field survey of what the values are on site is so much more accurate because it's real, as opposed to monkeying around with a model and trying to predict what's out there from 10 years ago or 15 years ago or whatever the hell it is. Right? So field measurements can be a very important and useful tool in establishing just what the heck's really going on somewhere. What are the light levels in the office really that they're working under now with a third of the lamps out and mismatched colors and yellowed lenses and, yada, yada, yada. Well, if they're working under this now, are they going to be okay with that? Do they want a little higher? Do they want to go back to what it was designed to begin with? Would that be too much now? Because they're used to half. I don't know. Field measurements could give you a starting point to look at for the work that you're going to do in that space, whether it be outdoors, indoors, upgrading, replacing, new design, whatever it might be. So running into a space, getting a grid of locations to get an average. I know a guy used to go out and do garages this way, right? He'd do an entire floor of a garage, hand measured after fixtures went in to make sure they were doing exactly what he thought they were going to do, as opposed to relying on the computer to do it. So field measurements can be very important, and they are accurate by definition, as opposed to this predicting what's out there already. Okay. And this is how you do it, right? On the right-hand side, luminance meters. You get a good meter. For indoor work, it's not as important how fine that meter can read light levels to. Outdoor work, it's super important. So the moon puts out 0.1 foot candles at times, right? So if you only have a plus minus of a half a foot candle on your meter, outdoor measurements are nothing. You just can't use it outdoors. I mean, you have to be at least 0.01 in terms of foot candles and how it can read them. And if it's accurate at those kinds of levels to go outdoors to measure foot candles at night, where you have minimums of 0.2 or 0.5 or 1, maximums under 10, right? And spill light requirements where cities don't want you to have more than point blank. Well, that means you got to be able to measure point blank accurately. So you have to have a decent meter to go. You have to have a better meter to go do nighttime stuff than you do daytime. Colorimeters, color spectrometers. I know early LED made use of those a lot to make sure that things were they were supposed to be. And then on the far left, a luminance meter. Those are super expensive, but they can, in a field of view, in a circle of X degrees, you can point those at building surfaces, ground surfaces, walls, and even at fixtures themselves to find out what their luminance value is. Remember candela per, or lumens per candela per square meter, then the luminance of the fixture. So intensity divided by the area of the fixture. The little circle in your view thing is the area. It does a back calculation of intensity and it tells you what it is. Oh, that brings us to another just minor point, but one that comes back to both all these things we're talking about in terms of luminance and sources and all this. The IES file, or the photometric report, right, that comes out from the lab, is going to have that candela value table. It's also going to tell you, quote, the luminous area of the fixture. And then that you use that luminous area divided by the candela table, depending on what angle you're looking at that area at, and you come up with luminance in candela per meter squared. But think of a 2x2 light fixture that goes up in the ceiling, right? Think of a panel 2x2 that's completely uniform all the way, luminance all the way across it. Oh, I guess my computer became unplugged. Hold on a second. Plug that back in so I don't lose you guys. So 2x2, lots of light all the way across it, right? That's probably pretty accurate, right? Candela value divided by the square area. Well, now you get a 2x2 that has this little tiny basket in the middle and all of the lights coming from that basket. Well, guess what? If the lumen value coming out of the 2x2 that's even, and the lumen value of the 2x2 with the bright stripe in the middle is even, and they're both reported as having areas of 2 square feet, they'll both have the same luminance value if you calculate it. Now you take this luminance meter in there and you shoot the 2x2 that's uniform all the way across, you might get a value close to what was reported. You shoot the one that's got the little stripe of light running down the middle, even though it's in a 2x2 pan, and your luminance value's through the roof because it's real and it's measured. So even the lead and the RP1 and all these things have these guidance for what the luminance of the source is. Even then that can be derailed by real life scenarios, right? Is that 2x2 coming out even all the way across, or is it a stripe in the middle? Because you take that luminance meter that we see on the left and you shoot the stripe. It's going to be 8 times what the reported value was. Things to think about in reporting and testing and complying with box checking across the way, right? If you're truly concerned about the luminance value of that fixture, maybe you don't pick the one with a stripe down the middle for all of its light. You pick the one that's even all the way across, right? So these are things to think about and that you can measure in real life. Same thing goes for outdoor fixtures, right? You've got an array of, I don't know, 50, 60 LEDs. The luminance value of that fixture is reported across that whole area divided, with the candle power value. But you take a luminance meter out there and you shoot one of those little LED spots, way brighter. So how do you ever enforce something about luminance outdoors when the calculational way of going about it is completely wrong compared to the real life measuring, right? Things to think about. All right, we talked about lumens, drops of light. Lumens onto an area, illuminance. Lux when it's onto a square meter, foot candles when it's onto a square foot. Bouncing light off of that in a diffuse fashion, foot lamberts, lumens off per square foot. Bouncing light out of that, really luminance, right? And then reflectance values of the surface that take care of all that stuff. All right, I think we've hit the end. Oh, we didn't do too bad on time, just short of 2 hours. All right, questions? Concerns? Did I talk too much?
No, very thorough, Bob. Thank you.
Anything burning about calculations? You already know my feeling about renderings.
Great. Well, thank you guys. Really appreciate it. Thank you, Bob, so much for your time as always. Very informative and amazing fundamentals of lighting.
Thanks.
So I think everybody has your contact information. So if you do have any follow-up questions for Bob, please don't hesitate to reach out, let him know. Again, a reminder, just with everybody on here, the session that will be in person has been rescheduled for to be at the lighting agency. So Allie said she sent out an email about that, so you should all have that information. But just so you guys hear it from me. But
And there are nuances around our facility in terms of parking. I forget what it's like on Saturday, but there's some spots across the street that are whole day. There's spots in the mornings that'll get you through noon. And then there's other spots that you actually have to pay for now. So be on the lookout for the signage.
cool. All right. Well, I hope everyone has a great night, and we'll see you at the next one.
All right. Goodbye, everybody.
Thanks, Bob.
Bye.
Bye.
Thank you, Bob.
Thank you,
Thanks,
Bob.
Bob.